Welcome friends to our session. In this video, I'll be taking you through chemistry for A level, and we are saying that chemistry for A level is divided into three. That is physical chemistry, organic chemistry, and inorganic chemistry. Specifically, in this session, I'll be taking you through physical chemistry, and we shall be having different sessions of these lessons until when all the topics, the subtopics are completed for physical chemistry, and also we shall be looking at organic chemistry. So for those who have not yet started following us, please click on the subscription button, and also you click on notification button so that whatever we upload, you'll be able to get it very fast. Also, when you find something very helpful, please don't forget to share and comment in the comment section. So in this session, and we shall be looking at physical chemistry, and here is the summary of what we are supposed to cover in physical chemistry at A level, advanced level. Number one, the first topic, that is moles and equations. We have thermochemistry, we have equilibria 1, we have equilibria 2, we have electrochemistry, and reaction kinetics. So these are the topics which are under physical chemistry. But don't forget that even organic chemistry has its own content that we're supposed to cover, and inorganic chemistry has its own content. We shall be bringing all these sessions one by one. Make sure that you always follow us. Click on notification button so that you can always have the update of what we are sharing. Let's go directly to topic number one, and that is moles and equations. So in this topic, it is divided into different subtopics. The first one is masses of atoms and molecules, then accurate relative atomic masses. This first subtopic is what you're going to be looking at in today's video. Then the second one, we shall be looking at amount of substance and mole calculations. Then another one, we shall be looking at chemical formulae and chemical equations. And finally, this will be our last subtopic to cover, which is solutions and concentration, then calculations involving gas volumes. Let's dive into our very first subtopic, that is masses of atoms and molecules, then accurate relative atomic masses. So what do we expect to have known by the end of this session? So by the end of this session, a learner should be able to evaluate the relationship between atomic masses and isotopic abundances in calculating accurate relative atomic masses. Number two, a learner should be able to synthesize methods to determine accurate relative atomic masses using given isotopic data. So those are the two learning outcomes, what we expect a learner to have known by the end of this session. Okay, so shall we begin by introducing to ourselves what we already know. At least we looked at something about atomic and molecular masses in ordinary level. So we shall be reminding ourselves of what atomic mass is, of what molecular mass is. They're saying that atomic mass is the mass of a single atom. It is a mass of a single atom, atomic mass, and it is expressed in atomic mass units. So the units of atomic mass is AMU. So the mass of a single atom, and by definition, we normally say that it is the mass which is occupied by 1 mole of a substance. In simple terms, when we talk about the molar mass. But here we're saying that atomic mass is just that mass of a single atom, while molecular mass is the sum of atomic masses of all atoms in a molecule. So from the word molecular, a molecule means more than one. So when you talk about molecular mass, it is a mass of a compound, or a compound which is consisting of more than one atom. And to get this mass, we are saying we get the sum of all the atomic masses of all the atoms in that molecule. Now, how important are these atomic masses and molecular masses? Here is what we're talking about. It is used in chemical calculations, in stoichiometry, and understanding molecular structures. For those who have not yet watched our video about stoichiometry, let's go back on the channel and you see how the atomic masses and molecular masses have been used in stoichiometry, how they have been used in understanding the different molecular structures. That has been explained very well in our previous videos. Now, what is the definition of relative atomic mass? You recall we are looking at determining relative atomic mass and also determining the accurate relative atomic mass. So I'm saying that relative atomic mass, which we are summarizing as RAM, RAM, is the weighted average of an element's isotopes compared to a 12th the mass of carbon 12. So that is a simple definition of relative atomic mass. We are saying that it is compared to the mass of carbon 12. In the previous session, when we are looking at mole concept, we are able to explain why among all the elements are they considering carbon 12. So in simple terms, we can summarize relative atomic mass as a summation of percentage abundance times multiplied by the respective isotopic masses divided by 100. We're just from here, elements isotopes. So we're looking at the summation of the abundance of each isotope times the respective isotopic masses. This is the first formula, but also it can be written as summation of relative abundance times the respective isotopic mass. This is for the case when they have not given you in percentage. This is when you have abundance in percentage and when you don't have it in percentage. We are going to see all this as we see how the accurate relative atomic mass is determined. How do you get the abundance? All this we are going to be looking at it in this session, and we shall be able to do different examples showing how we can calculate the relative atomic mass. So as you're saying, it is measured in atomic mass units, but as we said, for relative atomic mass, it does not have units because it is a ratio. It is a ratio of masses. Now let's look at another one, which is isotopes and their abundances. Isotopes and their abundances. What is an isotope? So saying that isotopes are atoms of the same element with different number of neutrons. But they have the same what? They have the same number of protons. So those are the ones we say are isotopes. It is atoms of the same element. For example, we have an example of carbon. Carbon has an atomic number of 6, but we have different isotopes of carbon, where the first one has mass of 12, another one has mass of 13, another one has mass of 14. So if this one has how many neutrons? You go to get this mass number, you get the neutron plus the protons. Now, we know that the proton number of carbon is 6. So when you get 12 minus 6, you get 6 neutrons. Then here 13 minus 6, you get 7 neutrons. While here we have 14 minus 6, that is 8 neutrons. So you can see carbon 12 has 6 neutrons, carbon-13 has 7 neutrons and carbon-14 has 8 neutrons. So those atoms of the same element with different number of neutrons are the ones we call the isotopes. So these are different isotopes of carbon. Then what is isotopic abundance? Isotopic abundance is the percentage of a particular isotope in a natural sample of the element. The percentage. So when you find out that when we get a sample of carbon and we pass it through an instrument which we use in determining the accurate masses, like mass spectrometer, you find out that the different isotopes, they have different percentages, they have different abundances, how they occur. You find that some are having a small percentage while others have a bigger percentage. So those percentages of a particular isotope is what we call a natural, or in a natural sample of an element is what we call the isotopic abundance. Now, we're looking at how do we calculate the accurate relative atomic mass. Relative atomic mass, the accurate one. So the first thing is to identify the isotopes and their masses. After that, we multiply each isotope's mass by its relative abundance. Then after that, we sum the products. We divide by the total abundance. So I believe we saw this calculation. We saw this in the previous here. We were looking at summation of relative abundance times the respective isotopic mass. And we say that we have the two methods. We shall be using the two methods to do the different calculations. And let's continue. So that is the method that we can use to calculate the accurate relative atomic mass. Those are just steps which you can follow, and we're going to do an example, and we use the same steps to get our accurate relative atomic mass. So we're saying that a mass spectrometer is used in determining the accurate mass of the substance. So one of the instruments that we normally use, or they use in calculating the accurate relative atomic mass, is the one we call a mass spectrometer. Let's have a look at a mass spectrometer. So here we have a mass spectrometer. The mass spectrometer is this diagram we're seeing here, and we're having an experiment to determine the relative atomic mass of the substance using a mass spectrometer. So we are going to go through this, and we have different stages. There are different stages that we can always have in our mind as we are looking at a mass spectrometer. We want to see how do we come to get the accurate mass of a given substance, right away from the sample until when we get our accurate mass of that substance. So we start from, we have 5 stages. Number 1 is vaporization. If any substance is not in vapor form, we don't put it into this machine. Instead, what we do is to first vaporize it. So the vaporization is number 1. Then from vaporization, we go to ionization. We ionize the sample into positive ions. Ionization. After that, we have the acceleration, where they are accelerated between electromagnetic fields. So that is another stage. Those are 3. The third one, you pass it through magnetic field. After passing it through magnetic field, our last stage is the detector. The detector, for it is used in detecting the ions. You call when we put a sample, it splits into its ions. So the detector here is the one to do that job. So we're going to go through each step step 1 until when we get our final answer. But this is our diagram, which is showing the mass spectrometer. So I've said that we have the 4 stages. Now I want us to start from here. Number 1 is ionization. But I say that before we go to ionization is vaporization. If a sample is not in vapor form, what we do the stage of vaporization. We vaporize the sample, and then the vaporized sample is the one which enters here. I believe you can see here is where the vaporized sample enters. When it enters here, then we go to our stage, which we call the ionization stage. Now in this stage here where we see electron beam, actually other books will find there electron gun, which means what is coming from there are electrons. You can see electrons heating. Then we have here heater vaporizes the sample. That is, if the sample is not in vapor form, it vaporizes. But if it is in vapor form, it enters. So that our very first stage we say it is vaporization. After that, we pass it at electron beam, where at this point the sample knocks out the electrons from the atoms or molecules, creating the positive ions. So when these electrons hit the sample here, this sample it spreads into ions. When there is that bombardment, the bombardment of electrons with the sample here. So when it hits the sample, it spreads into creating the positive ions. Now these positive ions are the ones which enter into this area. Now here you're seeing one that ions are accelerated. This area we call it electric field. In electric field, it is where there are some charges there. So these electrons, which positive ions which are coming from here, are directed to electric field. In this area, ions, the positive charged ions, are attracted towards the negative charged plates. So in this area between this plate and this plate, this is where we have the negative charged plates. So they are directed in this area, and then they are accelerated into a focused beam using an electric field. So it is between these two. That is what happens. In this area, just the ions are accelerated into a focused beam using the electric field. So after that, they are directed into the magnetic field. We can see the magnetic field here. We're seeing a magnet. Now this area where there is a magnet is what we call the magnetic field. What happens in the magnetic field? In magnetic field, what happens is deflection. The accelerated ions which are coming from this area, electric field, accelerated ions pass through a magnetic field, and the field deflects the ion path based on their mass charge ratio. It's based on the mass charge ratio. You recall different ions which are coming out are the ones which are going to give us the different isotopes of that sample. So when they come out, some are heavy while others are, depending on their masses. The one with a higher mass, it is heavy. The one with a lighter mass, smaller mass, it becomes the lighter one. So we're saying that light ions are deflected more than heavier ions. Those which are heavy, they are deflected less. While those the ones which are lighter, they are the ones which are deflected more. So which means when you check here, the first line here, it will be representing the ion, the positive ion of the sample, which is light, followed by this one, followed by this, followed by the fourth one, and the third one is the one which is heavy ion. Now we go to the last one, which is the detection stage. At the detection stage, now we are going to detect the ions which are coming from the sample. So at this stage is where we do what? We detect. So at this stage, what happens? The ions reach a detector where they generate an electrical signal. So when they reach at the detector, they generate what we call the electric signal. After that, the signal strength depends on the number of ions with specific mass to charge ratio. So this one. Then finally, the mass spectrum is produced, showing the relative abundances of each ion. So when it has been detected, a mass spectrum. Now, mass spectrum, it has been shown here on the side. This is the mass spectrum of this sample that we have recorded. And this mass spectrum, it is showing the mass to charge ratio, and the relative abundance. We already know what relative abundance is. We already know what mass to charge ratio is. Mass and charge ratio. So we can see here there are how many ions? 1, 2, 3, 4, 5. There are 5 ions. And even here, we find that we have 5 peaks. We have the first one, second one, the third one, the fourth one, and the fifth. Now, the one which is heavy, it is here. It is the one which comes last on this side, followed by this one, followed by this. The one which is lighter is the one which comes in first. Now, we are saying that when they are being detected, the signal strength depends on the number of ions with a specific mass to charge ratio. So when this detector is the one which gives us the abundance of each ion. So this first ion, this one here, it is the one which is represented with the mass of 90, and it has its abundance around there, 50 there, 51. Then the one with 91 mass, it has something. So it is a scale which is showing us the relative abundance. So here it is around 10. Then we have the one for 92, it is around 18. Then the one of 94, it is also around 18. Then the one with mass of 96, it is very low, for it is around there to abundance, percentage abundance. So we're saying all these values here are given, are read from the mass spectrometer right here at the stage of the detector. So that's where we are able to read all these, the mass and also the relative abundance. We are going to have some examples and we see how best we can calculate the accurate relative atomic mass using the information from the mass spectrometer. We can see that from the mass spectrometer, we just get a spectrum of that sample. Then after getting the spectrum of that sample, then we can do the calculation. Don't forget that the calculation, we saw the different steps we follow using our formula. Now, at this stage where we have magnetic field, we say that there are different factors which cause these ions to bend, to form these curves. The one which comes first, the one which comes second, the one which comes third, it is dependent on different factors. That's the one we are looking at. The extent of diffraction of each type of ion depends on a number of factors. Which factors are we talking about? Number one, we're saying that the stronger the magnetic field, the greater the extent of diffraction. So we're saying that if the magnetic field is very strong, even the rate at which these ions are curved, at which the diffraction takes place, it will be very high. That is the first. Number one, it depends on the strength of the magnetic field. Then number two is the mass of the ion. mass of the ion, and we're saying that the light ions are diffracted more than heavy ions of the same charge. So you have the ions of single charge, and there's the one which is having a small mass. Those ones which are having small mass are diffracted more than those ones which are having a bigger mass. So that is the mass of the ion. It is also affecting the diffraction of that particular ion. Then the last one is the charge on the ion. We can have those ions which are maybe positive 2, another one is positive 1. Now we are saying that a highly charged ion is diffracted more than the ions with single charge of the same element and same mass. They have the same mass, but the difference is the charge. Now, why is it that the highly charged ion is diffracted more than the one with a single charge? The reason is here. This is because the greater the charge on the particle, the more it is attracted or repelled by the charged body. So when the charge is higher, the attraction also is. This worked example. This is a worked example which is saying that the diagram below shows the mass spectrum of neon, and then they're saying calculate the relative atomic mass of neon. So after using the mass spectrometer, the detector, you had to read the spectrum. The spectrum was showing these values, showing us the mass of each isotope and its percentage abundance. Another question is, what is the relative atomic mass of neon after having all this data? So we have this method which we already have. We say that RAM can be summation of percentage abundance times relative isotopic masses of 100. So we have percentage abundance of each isotope and we have the respective isotopic masses. So the first one we have 90.9 times 20, 20 which is the mass, and then you have 0.3 times 21, then you have 8.8 times 22, then over 100. So when you multiply this, we get 1818 plus 6.3 plus 193.6 over 100. We can use our calculators to get those answers. Then finally we have 20.179. So therefore the relative atomic mass of neon is 20.179. So there we are able to calculate using the data that has been given to us. Okay, let's look at our second example. Our second example is still about the spectrum of neon. The diagram below shows the mass spectrum of neon. Calculate the relative atomic mass of neon. What is the difference between the first? This is the first example, then this is the second example. So the difference is that here they have given us relative abundance, but it's not in percentage. The first example, the relative abundance was in percentage. So when we have such a question, we can deal with it using two methods. We can use the one for just using relative abundance, and then we shall see another way we can deal with it using the percentage abundance by first calculating the percentage abundance. Let's go through faster. So I'm saying that relative atomic mass summation of relative abundance times relative isotopic masses divided by summation of relative abundance. So we can look at each isotope. The first isotope has relative abundance of 114 times mass, which is 20, plus 0.2 times 21, plus 11.2 times 22. We are getting abundance times respective isotopic mass. So when you add all that and calculate, you get 20.18. So this is our first method where we are using this. But also we look at the second method. This is the same question, example 2, but now we are looking at method 2. In this case, we are looking at summation of percentage abundance times respective isotopic masses of 100. So here in this question, they have not given us percentage abundance. So what we need to do is to first calculate the percentage abundance of each isotope. So how do we get percentage abundance? We first get the total relative abundance, which becomes 114 plus 0.2 plus 11.2. Here we get 125.4. And then after that, we can calculate the percentage abundance of each isotope. So that is saying that for isotope of mass 20, its abundance is 114. So we divide by with total abundance times 100. So we are able to get 90.91%. Then the second isotope is mass 21. It is having 0.2% over 125.4 times 100, and we get this answer. And then lastly, we have percentage abundance for isotope of mass 22. So it has abundance of 11.2. We divide by total abundance, which is 125.4 times 100. So we are able to get 8.93%. So after that, after getting the percentage abundance, then we can substitute in our formula. Percentage abundance times respective isotopic masses. So which means percentage abundance of the first one was 90.91 times its mass, which is 20, plus the second one is 0.159. We remove this 10 here. So it is 0.159 times 21. Then finally we have 8.93 times 22. So the answer, we're able to get 20.18. So therefore, relative atomic mass of neon is 20.18. So please, let's try other questions and we see how best we can get more knowledge and practice more questions about this. So in summary, we are saying that atomic and molecular masses, they help in chemical calculations, and relative atomic mass is a weighted average of isotope masses. Then we are saying that isotopic abundances determine the accurate relative atomic mass. And we are saying that let's practice calculating relative atomic masses using given isotope. Let's practice, and please, if you have any question about calculating relative atomic mass, make sure that you put it in comment section. Put it in comment section and I'll be there to guide you. I'll be there to direct you on how to calculate that question. I'll be bringing more questions on this topic, on this subtopic, so that we can continue to interact with more and look at different ways how we can solve those questions. Thank you for watching, and for any inquiry, maybe there's something which has disturbed you, or you need maybe like resourceful books for chemistry, practical, and also the theory books, don't hesitate to call on those numbers, or you WhatsApp. You can send a message on any of those two numbers and I'll be able to get you. I'll be waiting for you in our next session. Don't forget that you're moving a series by series until when we are done with A-level chemistry. Otherwise, have a blessed time. God bless.